Alright, hello everyone, and welcome to our last lesson for Unit 8, which is on pH and solubility. The main idea for this lesson is that solubility of certain salts can change depending on the pH of the solution. So we are going to be able to qualitatively predict how changing pH by adding acid or base will impact whether a salt dissolves more or less. And the wonderful part about this lesson is it's all about understanding what's happening. There's no calculations involved. So pH will only influence the solubility of a salt if one of its ions can react with hydronium or H plus or OH minus. This happens when the salt contains a conjugate base of a weak acid like acetate, a conjugate acid of a weak base like ammonium, or hydroxide ions. In these situations, adding acid or base will remove one of the ions from solution and shift equilibrium, therefore changing solubility. But if neither the cation nor the anion reacts with H plus or OH minus, then nothing is removed, no shift occurs, and the solubility is going to stay the same. And remembering back to Unit 7 when we introduced Le Châtelier's principle, it states that a system at equilibrium will adjust to minimize the impact of a disturbance or stress. So when we're talking about pH and how it affects a solubility of the salt, we're really going to be looking at what it's doing to those constituent ions. If we are increasing the ions, it's going to shift away from them. If we are decreasing the ions, it's going to shift towards the ions. So with this lesson, we work a lot with the dissolution of a ionic compound or a salt. So you do have to remember how to actually write out that equation. And that brings us back to when we learned about KSP, or the solubility product constant. So remember when we did KSP, you had your solid salt as your reactant, and then on the product side, you had your constituent ions. So something with a very high KSP means it's going to be very soluble and produce those ions. Something with a very low KSP is not going to produce a lot of ions and therefore be insoluble. So in order to practice that, let's go ahead and start with an example. Write the equation for the solubility of ammonium nitrate. So ammonium is NH4 plus, nitrate is NO3 minus. So our salt is going to be NH4 NO3, and that is going to be our solid salt. Then when we put that into water, it's going to break apart into NH4 plus, and now that we dissolved it in water, it's now aqueous, and NO3 minus aqueous. So this is how you would write out your equilibrium equation. All right, so let's look at the solubility of sodium fluoride. So if we are writing out the equation for the dissolution of sodium fluoride, we have the solid salt, and it would dissolve into Na plus ions and F minus ions. Now looking at my two ions, I can see that Na plus can come from a strong base, which is sodium hydroxide. And we know that when we use sodium hydroxide, it's going to fully dissociate into Na plus and OH minus. And we also know that Na plus is typically a spectator ion. And because it's coming from a strong base, we can assume that this is very weak or neutral. So because it's neutral, if we are increasing or decreasing the pH of the solution, meaning we're either adding concentration of H plus or hydronium, or adding concentration of hydroxide, Na plus is not going to want to react to those because it is stable and or neutral, however you want to think about it. So that means when we're looking at how pH affects solubility, we're really focusing on this F minus. And we know that F minus is the conjugate base of a weak acid HF. And we know if it's coming from a weak acid, the conjugate is usually pretty reactive. So if we were to decrease the pH, meaning we're adding in H plus or H3O plus, that is going to react with F minus to form HF. And by doing that, we are decreasing the concentration of F minus, which is going to shift the equilibrium to the right, increasing the solubility of NaF. Now, when we increase the pH of this system, it gets a little more complicated because when we increase pH, we are introducing OH minus. But as you can tell from this equation we have currently, we know Na plus does not want to react. So if we introduce OH minus, it's obviously not going to react with F minus either. So what is it going to do? And in order to understand that, we need to go back to the autoionization of water. So I use H plus for my reasoning, so I'm going to kind of keep that flow of things. And I have H2O ionizing into H plus and OH minus. Now, if you like to use H3O plus, you can also use this equation for the ionization of water, which is the same thing. It doesn't matter which one you use. I'm just going to be using the top one. Now, if I'm increasing pH, I am introducing hydroxide ions into this solution. And by increasing my hydroxide concentration, I'm going to be consuming H plus ions to form more water. And because I am consuming H plus ions to form more water, that means I have less H plus ions reacting with F minus to create HF, which means I have more F minus, and that means I'm going to shift the equilibrium to the left, decreasing the solubility of NaF. All right, so let's run through that one more time with a little more structure. So we have NaF and its solubility, and we're looking at what happens to that solubility when we lower pH or increase our protons or H3O plus ions. So by increasing our protons, we are going to form hydrofluoric acid, and that's because the H plus ions are going to neutralize our F minus ions to form HF. When we form HF, we are decreasing the concentration of F minus ions in this solution, which means because of Le Chatelier's principle, we are going to shift this towards that species, and by shifting it towards the ions, we are increasing the solubility of sodium fluoride. If we increase the pH of our solution, that means we are introducing more hydroxide ions. And because Na plus is a neutral ion that doesn't really want to react, and F minus is negative, so that's going to repel with OH minus, I need to look a little bit deeper into what OH minus is actually going to react with. And that leads me to the autoionization of water. So looking at our bottom equation, we can see that if we add OH minus ions, those are going to react with either H plus or H3O plus to form water. And by neutralizing that H3O plus, I now have less F minus converted into HF. So I'm actually increasing my concentration of F minus because I have less of it being converted into HF. And by increasing F minus, I'm going to shift the reaction back towards a solid, which then decreases solubility. All right, now let's look at the effect of pH on solubility of metal hydroxides. Now with metal hydroxides, this is going to be way more straightforward because hydroxide is one of the ions. So if we lower the pH or add more H plus ions, then those are going to react with OH minus to form water, and that will decrease the concentration of OH minus, which shifts the reaction towards the right, increasing the solubility of iron 3 hydroxide. Now, if we were to increase the pH or add hydroxide, that means we are increasing one of our products. And by increasing our product, Le Châtelier's principle states that we're going to shift away from that, which means we're going to decrease the solubility of iron 3 hydroxide. All right, and before wrapping up this lesson, let's do a couple example problems. This question says the dissolution of lithium phosphate at 25 degrees Celsius is represented by the equation in system 1. The phosphate ion is the conjugate base of the weak acid HPO42-, as represented by the equation in system 2. The molar solubility of a saturated solution of lithium phosphate is determined at different pH values. The results are summarized in the table. What will increase the solubility of the salt? Increasing or decreasing pH? So looking at the molar solubility of lithium phosphate, I know I have a greater solubility, because this is my highest number, at a very low pH. So I know I'm going to increase solubility as I decrease pH. Then it says, what happens when the pH is lowered? And if I'm lowering pH, that means I'm increasing my concentration of H plus ions or hydronium ions. And because hydronium is in system 2, we're going to be using hydronium. So by increasing hydronium, I know I am reacting with phosphate ions to produce my weak acid and water. And because of that, I am decreasing my number of phosphate ions. And because of that, this equilibrium is going to shift towards that phosphate, which would increase the solubility of our salt. All right, and then looking at the table, what happens to the solubility of magnesium carbonate as pH decreases? So looking at moles of HCl added, I know that I'm really looking at my concentration of H plus ions. So the more HCl added, the more H plus I'm adding, which means the lower the pH. So here at the bottom, I'm going to have my lowest pH. So as I am decreasing pH, you can see that I am increasing solubility. So the question says, what happens to the solubility of magnesium carbonate as pH decreases? There will be an increase in solubility. And just to make sure we understand, let's go ahead and explain why decreasing pH increases the solubility. So by decreasing pH, I'm increasing my concentration of H plus ions. And looking at my two ions, I know that if I'm increasing H plus, it's going to want to be attracted to something with a negative charge, right? So I'm looking at CO3 2-, which is carbonate. Now, I know that carbonate came from HCO3 minus, which is bicarbonate and a weak acid. And if I have a conjugate of a weak acid, I know that it's attracting a proton pretty readily. And because of that, when I add in H+, it's going to bind to this carbonate to produce my bicarbonate, which is a weak acid. And because I am decreasing my amount of carbonate, that means this equilibrium is going to shift to the right, which increases the solubility of magnesium carbonate.